Hello, my name's Gabe. For this problem, we're given a logistic equation which models the growth of a population, and we're asked to find the value k, the carrying capacity, the initial condition, and then we're asked when will the population reach 50% of its carrying capacity, and then finally we're asked to find a differential equation which has solution p of t. So looking at our logistic equation, we want to note that this is in the form L divided by 1 plus b times e to the negative kt. This will help us as we work through the first few parts of the problem. So first, we're asked to find k. So looking at this problem, we see that k is equal to 0.75. Next, we're asked to find the carrying capacity. Well, we know that in this case, the carrying capacity is L. So looking at our logistic equation, we see that L is equal to 2100. So we have the carrying capacity, L, is equal to 2100. Next, we're asked to find the initial condition of our logistic equation. So to find the initial condition, all we want to do is find P of 0. So we're going to substitute 0 in for t. So P of 0 is 2100 divided by 1 plus, substituting 0 in for t, we'll have 29 times 1, which is 29. So P of 0 is 2100 divided by 30, which is 70. So the initial condition is P of 0 equals 70. Now for part D, we're asked to find when will the population reach 50% of its carrying capacity. So here we want to note that the carrying capacity was 2,100. So half of the carrying capacity would be 1,050. And we're trying to solve the equation, well, when is the population equal to 1,050? So that gives us the equation 1,050 equals 2,100 divided by 1 plus 29 times e to the negative 0.75 t. So what we can do here is we can divide both sides of this equation by 2,100, and that leaves us with the equation 1/2 is equal to 1 divided by 1 plus 29 e to the negative 0.75 t. So at this stage, we can go ahead and we can cross multiply, which gives us 1 plus 29 e to the negative 0.75 t is equal to 2. We can subtract 1 from both sides of this equation, which leaves us with 29 e to the negative 0.75 t is equal to 1. Divide both sides of this equation by 29. Here, in order to solve for t, we have to take the natural log of both sides of this equation. And this leaves us with negative 0.75 t is equal to the natural log of 1 divided by 29. And finally, to solve for t, we'll divide both sides of this equation by negative 0.75, leaving us with t is equal to the natural log of 1 divided by 29, all divided by negative 0.75. So this is the exact time at which the population will reach 50% of its carrying capacity. We can approximate this by evaluating this in a calculator. And we see that this is approximately 4.49 years. So after 4.49 years, we know that our population will be at 50% of its carrying capacity. Now for part E, we're asked to set up a differential equation which has a solution P of t. Well, we know differential equations, which give us the logistic equation, are given by dp dt is equal to k times p times 1 minus p divided by L. Well, we've already found k to be 0.75, and we found L to be our carrying capacity of 2,100. So we just need to substitute these values in, and we have dp dt is equal to 0.75 times p times 1 minus p over our carrying capacity, L, which is 2,100. So there we have a differential equation whose solution is P of t. Thank you.